For a 120/208 volt 3-phase 4-wire 250 amp distribution panel located 800 feet from the electrical room, calculations indicate the need for parallel runs of number 350 MCM per phase. To accommodate the parallel runs of number 350 MCM cables and other conductors, two 3-inch conduits are required. Each conduit will contain 3 runs of number 350 MCM cables, one for each phase, one run of number 350 MCM cable for the neutral, and one run of number 250 MCM bare copper grounding conductor. It is important to use THHN or THWM-2 conductors rated for 208 volts or higher. Install the conduits parallel to each other, spaced at least 6 inches apart. Pull the conductors into the conduits and terminate them securely. Ground the system properly. Use appropriate cable ties or clamps to secure the conductors within the conduits. Always consult the latest code requirements and manufacturer guidelines for accurate calculations. It is recommended to derate the conductors by 25% due to the long distance of 800 feet. The selection of appropriate conduit size and conductor type is crucial for ensuring the safe and efficient operation of the electrical system. Firstly, understanding the purpose of parallel conductors is important. When the ampacity requirements exceed the maximum allowable ampacity of a single conductor, multiple conductors can be run in parallel to effectively increase the current carrying capacity. This is often more practical and cost-effective than using a single, very large conductor. Secondly, the National Electrical Code, or NEC, provides specific guidelines for paralleling conductors. Section 310.10 addresses requirements for conductors in parallel. These requirements are designed to ensure that the paralleled conductors share the load equally and that the installation is safe. Conductors must be the same length, conductor material, cross-sectional area, and insulation type. Terminations must be made in the same manner. This ensures that each conductor carries its fair share of the current, preventing overheating and potential fire hazards. Thirdly, conduit size is another critical aspect of the installation. The NEC specifies the maximum number of conductors allowed in a conduit based on the conductor size, insulation type, and conduit type. The purpose of these regulations is to ensure adequate space for heat dissipation and to prevent damage to the conductor insulation during installation. Tables in Chapter 9 of the NEC, such as Table 4 and Table 5, are used to determine the allowable fill percentage for conduits. These tables take into account the cross-sectional area of the conductors and the internal area of the conduit. Fourthly, conductor insulation types, such as THHN and THWN-2, are important considerations. THHN, which stands for thermoplastic high heat resistant nylon, is a popular choice for electrical wiring. It has a high heat resistance rating, making it suitable for use in dry locations at temperatures up to 90 degrees Celsius. THWN-2, which stands for thermoplastic heat and water resistant nylon-2, is similar to THHN but is also suitable for use in wet locations. It has a moisture-resistant insulation, making it ideal for environments where moisture may be present. Both THHN and THWN-2 are commonly used in conduit installations due to their durability and versatility. Fifthly, grounding is an essential safety measure in any electrical system. Grounding provides a low impedance path for fault current to flow back to the source, allowing overcurrent protection devices, such as circuit breakers or fuses, to quickly trip and interrupt the flow of electricity. This helps to prevent electrical shock hazards and damage to equipment. The grounding conductor should be sized according to NEC Table 250.122, which is based on the size of the ungrounded conductors. In this case, a number 250 MCM bare copper grounding conductor is specified, which is appropriate for the size of the number 350 MCM phase conductors. Sixthly, conductor derating is a critical step, especially for long conductor runs. When conductors are run over long distances, voltage drop can become a significant issue. Voltage drop occurs when the voltage at the load end of the conductor is less than the voltage at the source end. This can cause equipment to operate inefficiently or even fail. To compensate for voltage drop, conductors may need to be upsized. The recommendation to derate the conductors by 25% due to the long distance of 800 feet is a way to address this issue. By using larger conductors, the resistance of the circuit is reduced, which minimizes voltage drop. Seventhly, installation practices play a crucial role in the overall safety and reliability of the electrical system. Conduits should be installed in a neat and workmanlike manner with proper support and spacing. The NEC requires conduits to be securely fastened to structural elements to prevent movement and damage. The recommendation to space the conduits at least 6 inches apart is likely intended to improve heat dissipation and prevent the conductors from overheating. Eighthly, pulling conductors into conduits can be a challenging task, especially with large conductors like number 350 mcm. It is important to use appropriate pulling lubricants to reduce friction and prevent damage to the conductor insulation. The conductors should be pulled smoothly and evenly to avoid kinking or stretching. Once the conductors are in place, they should be properly terminated at both ends. This involves stripping the insulation, crimping or torquing the connectors, and ensuring that all connections are tight and secure. Ninthly, the use of cable ties or clamps to secure the conductors within the conduits is another important detail. These devices help to keep the conductors organized and prevent them from shifting or rubbing against each other. This can help to prevent damage to the insulation and reduce the risk of electrical faults. Cable ties should be made of a durable, non-conductive material and should be properly tightened to provide a secure hold. Tenthly, documentation is a critical but often overlooked aspect of electrical installations. Accurate records should be kept of all conductor sizes, conduit types, and other relevant information. This documentation can be invaluable for troubleshooting and maintenance purposes. It is also important to comply with all applicable codes and regulations. Electrical inspections are typically required to ensure that the installation meets the NEC and other local requirements. Proper planning, careful execution, and attention to detail are essential for successful and safe electrical installation. By following the guidelines and recommendations outlined above, it is possible to create a reliable and efficient electrical system that meets the needs of the application. In summary, the installation of parallel conductors for a 208-volt three-phase system involves careful consideration of several factors, including conductor sizing, conduit sizing, conductor insulation types, grounding, conductor derating, and installation practices. By following the NEC and other applicable standards, it is possible to create a safe and reliable electrical system. The NEC provides specific guidelines for paralleling conductors, ensuring that the paralleled conductors share the load equally and that the installation is safe. Conduit sizing is another critical aspect of the installation. The NEC specifies the maximum number of conductors allowed in a conduit based on the conductor size, insulation type, and conduit type. Conductor insulation types, such as THHN and THWN-2, are important considerations. THHN is suitable for use in dry locations, while THWN-2 is suitable for use in wet locations. Grounding is an essential safety measure in any electrical system. Grounding provides a low impedance path for fault current to flow back to the source, allowing overcurrent protection devices to quickly trip and interrupt the flow of electricity. Conductor derating is a critical step, especially for long conductor runs. To compensate for voltage drop, conductors may need to be upsized. Installation practices play a crucial role in the overall safety and reliability of the electrical system. Conduits should be installed in a neat and workmanlike manner with proper support and spacing. Pulling conductors into conduits can be a challenging task, especially with large conductors. It is important to use appropriate pulling lubricants to reduce friction and prevent damage to the conductor insulation. The use of cable ties or clamps to secure the conductors within the conduits is another important detail. These devices help to keep the conductors organized and prevent them from shifting or rubbing against each other. Documentation is a critical but often overlooked aspect of electrical installations. Accurate records should be kept of all conductor sizes, conduit types, and other relevant information. Proper planning, careful execution, and attention to detail are essential for a successful and safe electrical installation. Remember to consult the latest edition of the National Electrical Code and any local amendments for the most up-to-date requirements. Always prioritize safety and consult with a qualified electrical professional if you have any questions or concerns. The calculations for conduit fill are crucial to prevent overheating and ensure the longevity of the conductors. The NEC provides tables that specify the maximum allowable percentage fill for different types of conduits. These tables take into account the size and number of conductors, as well as the internal diameter of the conduit. Exceeding the maximum allowable fill can lead to increased heat buildup, which can degrade the insulation of the conductors and potentially cause a fire. When calculating conduit fill, it's important to consider the cross-sectional area of all conductors within the conduit, including insulated conductors, bare grounding conductors, and any other cables or wires. The total cross-sectional area of all conductors should not exceed the maximum allowable fill percentage for the selected conduit size. In addition to conduit fill, it's also important to consider the bending radius of the conduit. The NEC specifies minimum bending radii for different types of conduits to prevent damage to the conduit and conductors during installation. Sharp bends can cause the conduit to kink or collapse, which can restrict airflow and make it difficult to pull conductors through the conduit. The minimum bending radius is typically expressed as a multiple of the conduit diameter. For example, a 2-inch conduit might have a minimum bending radius of 6 times the conduit diameter, which would be 12 inches. Proper grounding techniques are essential for ensuring the safety of the electrical system. The grounding system provides a low impedance path for fault currents to flow back to the source, allowing overcurrent protection devices to quickly trip and interrupt the flow of electricity. This helps to prevent electrical shock hazards and damage to equipment. The grounding system typically consists of a grounding electrode, such as a ground rod or a metal water pipe, connected to the equipment grounding conductors. The equipment grounding conductors are connected to the metal enclosures of electrical equipment and provide a path for fault currents to flow back to the source. The size of the grounding conductors should be based on the size of the ungrounded conductors, as specified in NEC Table 250.122. It's also important to ensure that all grounding connections are tight and secure. Loose or corroded connections can increase the impedance of the grounding path, which can reduce the effectiveness of the grounding system. Regular inspections and maintenance of the grounding system are essential for ensuring its continued effectiveness. In addition to grounding, bonding is another important safety measure. Bonding involves connecting together all metal parts of the electrical system to create a continuous electrical path. This helps to equalize the voltage potential between different metal parts, which can reduce the risk of electrical shock hazards. Bonding conductors should be sized according to NEC Table 250.102. It's also important to ensure that all bonding connections are tight and secure. Proper installation of the conductors within the conduit is crucial for ensuring the longevity and reliability of the electrical system. When pulling conductors through the conduit, it's important to use a pulling lubricant to reduce friction and prevent damage to the insulation. The pulling lubricant should be compatible with the conductor insulation and the conduit material. It's also important to avoid pulling the conductors too hard, as this can stretch or damage the conductors. After the conductors have been pulled through the conduit, they should be properly supported and secured within the conduit. Cable ties or clamps can be used to secure the conductors and prevent them from shifting or rubbing against each other. The conductors should also be properly terminated at the electrical equipment. This involves stripping the insulation, crimping or torquing the connectors, and ensuring that all connections are tight and secure. Regular inspections and maintenance of the conductors and terminations are essential for ensuring the continued reliability of the electrical system. The long distance of the conductors can have a significant impact on the voltage drop in the circuit. Voltage drop is the decrease in voltage that occurs as electricity flows through a conductor. The amount of voltage drop depends on the length of the conductor, the size of the conductor, and the amount of current flowing through the conductor. Excessive voltage drop can cause equipment to operate inefficiently or even fail. To minimize voltage drop, it's important to use conductors that are large enough to carry the required current over the long distance. The NEC provides guidelines for calculating voltage drop in Chapter 9, Informative Annex D. These guidelines can be used to determine the minimum conductor size required to limit voltage drop to an acceptable level. In addition to using larger conductors, other methods can be used to reduce voltage drop, such as using parallel conductors or increasing the voltage of the circuit. The choice of method will depend on the specific application and the available resources. The type of conduit used can also have an impact on the performance of the electrical system. There are several different types of conduits available, each with its own advantages and disadvantages. Rigid metal conduit, or RMC, is a heavy-duty conduit that is typically made of steel or aluminum. RMC provides excellent protection for conductors and is suitable for use in harsh environments. Intermediate metal conduit, or IMC, is similar to RMC but is lighter in weight. IMC provides good protection for conductors and is suitable for use in many applications. Electrical metallic tubing, or EMT, is a lightweight conduit that is typically made of steel or aluminum. EMT is easy to install and is suitable for use in dry locations. Flexible metal conduit, or FMC, is a flexible conduit that is typically made of steel or aluminum. FMC is used to provide flexibility in electrical systems and is suitable for use in tight spaces. The choice of conduit type will depend on the specific application and the environmental conditions. Always consult the NEC and local codes for specific requirements. Consider the ambient temperature when selecting conductors and determining ampacity. Higher ambient temperatures can reduce the ampacity of conductors. The NEC provides tables for adjusting ampacity based on ambient temperature. Ensure all equipment is rated for the available fault current. A fault current is the amount of current that would flow in a short circuit. Equipment must be able to withstand the available fault current to prevent damage or injury. Perform a short circuit study to determine the available fault current at various points in the electrical system. Install surge protection devices to protect sensitive electronic equipment from voltage surges. Voltage surges can damage or destroy electronic equipment. Surge protection devices can help to protect equipment from these surges. Regularly inspect and maintain the electrical system to ensure it is operating safely and efficiently. Regular inspections can help to identify potential problems before they become serious. Maintenance tasks such as tightening connections and cleaning equipment can help to extend the life of the electrical system. Proper labeling of all electrical equipment is essential for safety and troubleshooting. Labels should clearly identify the equipment and its function. Labels should also indicate the voltage and current ratings of the equipment. Maintain accurate documentation of the electrical system, including drawings, specifications, and maintenance records. This documentation can be invaluable for troubleshooting and maintenance purposes. Follow all applicable safety procedures when working on electrical equipment. Always de-energize equipment before working on it. Use appropriate personal protective equipment, such as gloves and safety glasses. Be aware of the potential hazards of electricity and take steps to avoid them. Obtain the necessary permits and approvals before starting any electrical work. Electrical work typically requires permits from the local building department. Ensure that all work is performed by qualified electricians. Qualified electricians have the training and experience necessary to perform electrical work safely and correctly. Comply with all applicable codes and regulations. Electrical work is subject to numerous codes and regulations. Ensure that all work complies with these requirements. Consider future needs when designing the electrical system. Design the system to accommodate future growth and changes. Use high-quality materials and equipment. High-quality materials and equipment will last longer and perform better. Properly size the neutral conductor to accommodate nonlinear loads. Nonlinear loads, such as electronic equipment, can cause harmonic currents to flow in the neutral conductor. These harmonic currents can overload the neutral conductor if it is not properly sized. Provide adequate ventilation for electrical equipment. Electrical equipment generates heat. Adequate ventilation is necessary to prevent overheating. Consider the impact of the electrical system on the environment. Use energy-efficient equipment and design the system to minimize energy consumption. Promote electrical safety awareness among employees and the public. Educate employees and the public about the potential hazards of electricity and how to avoid them. Regularly review and update the electrical safety program. The electrical safety program should be reviewed and updated regularly to ensure that it is effective.